Hello, everyone, and good morning and good afternoon and good evening, actually, this time around, because we have some colleagues joining us from India. It's my great pleasure to introduce Rajesh Sundaresan, who is a professor at the Indian Institute of Sciences. And he's going to give us a talk on the work that he and his colleagues have been doing in India regarding testing. And I think his colleague Siva Atreya is actually online as well with him, as you could just see his name. Just a brief background, Rajesh did his bachelor's from Indian Institute of Technology, Madras. I didn't overlap with him, but he was there. It's the same school that I went to. The big difference is that while I was really messing up things, Rajesh was doing very well at the school. He went on to do his PhD at Princeton in communication networks, if I understand right, Rajesh, and then came back and joined IISc as a professor. He is really prolific, very wide range of interests. He's actually going to spend his sabbatical year at Strand and the Indian Statistical Institutes in Bangalore. So Rajesh, take it away. Thank you very much for joining us today and giving this talk.
Thanks for the invitation and for the introduction, Madhav. So I'll speak about optimal design of serosurveys for disease burden estimation. This is actually work with a large team from the Indian Indian Statistical Institute, Indian Institute of Public Health, Indian Institute of Science, and Strand Life Sciences. Today's presentation is based on a paper that we wrote and put on archive recently. It's available at this link. My co-authors, one of them is here, Shiva Atreya. There are other co-authors as well, Girdhar Babu, Aniruddha Iyer, Mohammed Minhas, Nihesh Rathod, Sharat Sriram, Nitin Vaidyan, and Sarat Yashodhan. We have a large team, and each of us has been funded by one or the other of these sponsors. So thanks to them for their sponsorships. So let me begin with an introduction. So for devising evidence-based public health management strategies, we often need to estimate the total prevalence of a disease, and in this context, COVID-19, in a particular locality. And this is important for determining at what rate we should be testing, how many tests per day should we conduct in an area, or at this advanced stage of the disease, when we have vaccines, what should be the vaccine allocation? So if we have these disease burden estimations, then we can appropriately allocate vaccines, for example. This is usually done via serological surveys. And in these serological surveys, we try to detect antibodies that survive for some length of time, immunoglobulin G or IgG. And these are ones that become detectable 2 to 3 weeks after exposure. I'll now give a context for the work and also about issues related to just doing serological surveys. So this is India, and Karnataka is over here. Karnataka is a state with about 70.7 million estimated population for 2020. And it's about 192,000 square kilometers. So that's about 80% of the United Kingdom. And about 12.4 million people live in Bangalore. That's on this southeast corner. Let's say that we are to conduct a serological survey in Karnataka. Actually, we did conduct a serological survey in Karnataka, and we did this during September 2nd and September 16th. So that's the period. And this is the number of confirmed cases in Karnataka starting from around March. So things were under control, and then slowly it started rising. In July, it really started picking up. And around the time when we were doing the serological survey, there was actually quite a bit of active infection. It peaked on October 8th or 9th. And then from then on, we've been seeing a decay. And we hope it remains this way. So this picture is taken from COVID19india.org, a volunteer group that has been publishing a lot of these details for various states in India. So what's the issue with serological surveys? Serological surveys alone would not have sufficed in the Karnataka context, particularly when we were doing the survey, because we would have missed a lot of those with active infection at the time of the survey. So we were near the peak when we did the survey. So therefore, one must estimate seroprevalence as well as active infection when the active infection is high. Otherwise, our estimates are going to be delayed. It would be something that was maybe 2 weeks earlier than the time of the survey. When we do this joint estimation of past infection as well as active infection, then we can write down the total burden as at the end of the survey as the sum of these two estimates. But To capture past infection as well as active infection, we need to conduct different types of tests. Let me describe those tests. So this is a picture taken from one of the papers in Nature group. So here is the PCR test that will capture viral RNA. And this can be positive for a long period of time, even after the person stops being infectious, but it captures viral RNA. There is also another test, the antigen test, which captures viral proteins when the person is most infectious. And then there are these antibody tests, and we'll focus on the IgG antibody test, which lasts for weeks, if not months. So these are three tests that could be conducted. So when we conduct a survey, we want to conduct, let's say, not just the IgG test, not just the serological survey, but we also want to check whether they have active infection or not. So when we recruit participants, what tests do we administer? Do we do only the RT-PCR tests on a particular participant, or only the RAT, or only the IgG test, or maybe a combination thereof? And also, how many participants do we recruit, maybe for each of those combinations? So these are the questions that we would like to address. So what are the considerations in trying to answer this question? So here are some approximate test costs, and these are as of early December. The antigen test costs about 450 rupees. So a US dollar is about 75 rupees. So that is about $6. The RT-PCR test is about $22 to $23, and the IgG test is about $4. So 1,600 rupees and 3,000 rupees. Ideally, from a statistical perspective, we would like to sample as many as possible, but cost considerations will limit the number that we will recruit. Also, these tests that we use are not completely reliable. So let's begin with the IgG ELISA kit. It has a sensitivity of about 92.1% and a specificity of about 97.7%. The RT-PCR test has a sensitivity of about 95%. And this takes into account the possibility that the sample may not have been grabbed properly, or there could have been transportation issues, or the specificity is not 100%. In our calculations, we have taken 97%, taking into account the possibility of contamination and inconclusive outcomes. And the antigen test, unlike these two, is somewhat poor in its sensitivity, only about 50%. The specificity is about 97.5%. So the tests are not reliable, and that's another, and they have varying reliabilities. And what proportion of the antigen test should be used, etc., are all dependent on this. Okay, so let's dive into some definitions to get a feel for how to go about designing an optimal survey. So suppose there are three tests, and let's take these three tests to be the antigen test, the RT-PCR test, and the IgG ELISA test. A test suite T is a subset of tests that's done on a participant. There are several possibilities. So if there are three tests, for example, you might either conduct the RAT or not, or you might conduct the RT-PCR or not, and so on. Therefore, there are a total of 8 possibilities, and all these possibilities, the possible suite of tests, I'll call that as capital T. Okay, so here is an example to explain what I mean by test suites. I denote by T a test suite. It's something which is T1, it's a triple T1, T2, T3. If one of these is 0, then that test has not been done on this participant. If it is 1, that test has been done. 1 is for the antigen test, 2 is for the RT-PCR test, and 3 is for the IgG test. So take this example here. Here is an individual on whom all 3 tests have been done. So 1, 1, 1. So the test suite is do all the 3 tests on this particular individual. Here is another individual on whom the antigen test has not been done, but the RT-PCR and the IgG have been done. Here is a third participant on whom the RT-PCR has not been done, but the other 2 has been done. And on this last participant, the IgG has not been done, the other 2 have been done. So this is the test suite that was employed on individual number 5 and so on. The outcomes will be appropriately identified. So for example, if an antigen test was not done, there's no antigen test outcome, but for the others, there would be an outcome. A 0 indicates that it was a negative test, and 1 indicates a positive test. And so here there are a total of 27 possibilities, because each outcome could be either negative or positive, or if the test was not done, and not applicable outcome. So 27 possibilities here. So this is a test suite, and these are the corresponding outcomes for that. I'll now describe survey design, cost, and performance. The survey design Just it's a bunch of numbers that indicates how many participants, let's say WT, will be administered a test suite T, and this is for every test suite. So it's a collection of a number of participants for each test suite. And the cost of this design is, what is the cost of this test suite? So that, let's say that that's CT for test suite T. And CT itself is made up of, let's say, all the three tests. Then you sum up the three individual costs. So if CT is made up of two tests, you sum up the cost of those two tests alone. So CT is determined once you have the individual costs and the test suite. And if there are WT members that are administered test suite T, then CT times WT is the cost for administering test suite T, and then you sum it up across all the possibilities. And that's the overall cost of this design.
Yes, Ajay, just one quick clarifying question. So T is basically the triple. Which of the tests?
T is this triple, yes.
Okay, good, sorry.
Yeah. And the cost of this triple is only two tests were done. So that would be about 450 rupees plus about 1,600.
Okay, so that's linear.
That's linear, yes. Okay, so that's the survey design, the WT, the set of WTs. The cost is just linear in this cost, and CT itself is linear in the test costs. So what's the performance of this design? To answer the performance question, I'll first have to address a statistical question. So let's look at that. So I give you this sort of a line list associated with the survey. So we conducted this survey. We had these 5 individuals. The test suite on the first individual was all the 3 tests, and this is the outcome and so on. In the surveys that we conduct, there are about 16,000. There were 16,000 in the September survey, and we are conducting a second survey now. There are about 40,000 in the second survey. So we have a line list like this, which indicates what is the suite of tests done on each individual and what are the outcomes. So how do you go about estimating the total burden from this design and outcomes? So we are also given a fixed design. Now I'll highlight the issues. The issues are that there is variation in the test suites across participants for a given design. So if we chose a certain design, we have to take that variation into account. That means that some outcomes are not going to be available simply because we didn't do those tests. The other issue is that the test outcomes are noisy, and we'll have to account for those. A possible strategy to handle these estimations would be to look at what's the active infection. So that, for example, you could look at the OR of these 2 columns that would tell us how many people are actively suffering from this infection now. So in this example, there is 1 here, a second person and a third person, and 3 out of 5. So you could do a count like this and say that 3 out of 5 have active infection and 1 out of 5 had infection in the past. You could come up with an estimate like this. That would be a simple estimate, but these counts by themselves do not use all the information that's available. Let's take an example of this individual 2 here, whose IgG outcome is 1. So this individual came out positive on the IgG test. Of course, it's a noisy outcome, but the fact that the RT-PCR outcome came as 0 will actually enhance evidence for this person to have had the infection in the past. And vice versa, the fact that the person came out positive on the IgG outcome will enhance the evidence on this noisy RT-PCR test outcome. And so we need to take into account all the outcomes on each individual and somehow use that information more efficiently, which mere counts do not do all that well. So how do we use this information that's available? For this, I need to describe a model. So here is a simple model and what the ideal test outcomes would be under that simple model. So let's dive into this model. So in this model, we assume that each individual could be in one of 4 different states. I'll call that 1, 2, 3, 4 here, S for state. In the first state, the individual has only active infection, but the individual has not yet developed any antibodies. In the second state, the individual has had past infection, but doesn't have any active infection, and he has developed antibodies. In the third one, the individual is in this intermediate stage where there is still viral RNA or maybe viral proteins, but IgG is also showing presence as well. And this could, for example, happen because the viral RNA can stay on for a long time. And in the fourth state, the person shows no active infection and no antibodies. So we assume in the simple model that these are the four possible states. If you look at the population as a whole, we assume that P1 fraction is in this state, P2 fraction is in this state, P3 fraction in the state where both IgG and active infection is present, and P4 fraction where there is neither active infection nor IgG. That means that if you're looking for what fraction of the people have suffered in the past or are actively suffering from this infection, we have to take the first three things and we'll have to sum them up. So that's P1 plus P2 plus P3. So if we can somehow, from the line list and the observations, find out what the best estimates for P1, P2, P3 are, then we can just sum them up and then get the best estimate for the total burden. So that's the strategy, somehow to get this P1, P2, P3. Unfortunately, what we have at our disposal is only these test outcomes, which are noisy. We don't have these hidden states. And we would like to infer these hidden states, or at least the fraction of people in each of these hidden states. So that can be viewed as a state and an outcome in the form of this tandem channel that takes into account an ideal outcome and then a noisy outcome. So I'll now go back to this ideal outcome, and then I'll come to describe the noisy outcome. That will describe the composite tandem channel. So when a person is in state with active infection, the rat will ideally put out a 1, will put out a positive outcome. The RT-PCR will ideally put out a positive outcome, and the antibody test, the ELISA kit, will ideally put out a negative outcome. Similarly, in state 2, these two will be negative, but the IgG ELISA kit would put out a positive outcome. In this intermediate stage, all the three will put out a positive outcome, and in the last state, none of these will be positive. So these are the ideal outcomes, and of course, we don't get this ideal outcome always. Here are the ideal outcomes. So let me look at the state 1 and 3. They correspond to active infection only, or active infection and IgG antibodies. And so the rat, this is for the rat. The rat will turn out to be positive on these two states and negative on these two states. So that's the ideal outcome. And similarly, there are ideal outcomes for the other two. And then there is the noisy binary channel. It's an asymmetric channel that describes the outcome given this hidden state, given the ideal outcome. And these are, so the weights on these branches are 1, that's on the left channel. And on the right channel, we'll need to use the sensitivity and the specificities, and those are the ones that appear here. Okay, so that's the nice way to look at this, and then this kind of will make it clear how to estimate what the probabilities of outcomes are given the hidden state. And one can write this in this particular form. So these are the transition probabilities. So if a person is in hidden state, let's say active infection only, what's the chance that the antigen test gives out a negative outcome? And what's the chance that it gives out a positive outcome? And if multiple tests are done, let's say the antigen test and the RT-PCR test is done on this individual, what's the chance that this could be a 0 and this one could be a 1? So you can write this by following the branch to this particular outcome from the state, and then write out the transition probability. And if 2 tests are done, you take the product of the possible outcomes. And that's exactly what is given in this expression here. So that tells you what the probability of an outcome is given the state of the individual. Now, how do we use this in our parametric model? We just recognize that the states are hidden and these parameters P1, P2, P3 are unknown. So that's what is indicated here. The 4 disease state probabilities with the parameterization P1, P2, P3 are P1, P2, P3, and P4, which is 1 minus the sum of the other 3. P1 plus P2 plus P3, recall, is the total burden, or the number of people who have suffered the infection in the past or are suffering the infection at this moment. So let's parameterize the system with this P1, P2, P3. The disease state probabilities are these, and every individual that is sampled from the population is such that the disease states are independent and identically distributed according to this. So that's the assumption that we will make. Now, for each individual, we will know if the test suite is known for this individual, if the design is a fixed design. then we know for this individual, these were the tests that were administered. So some test suite. And the test outcomes are y of n, let's call it y of n. This is t of n. What's the likelihood of this observation given that the test pattern that has been used on this individual is t of n? Well, we know the likelihood if we know the hidden state. So that would be this. But we just marginalize the hidden state based on these parameters, P1, P2, P3, and P4. And that gives us the outcome given that the test pattern is this and when the parameters are P. So this gives us a parametric model for the system. So when we sample an individual, if the P1, P2, P3, the underlying probabilities are these, then the outcome, the observation y of n, given the test pattern t of n, is given by the simple linear expression in the unknowns, where these transition probabilities are all known. So these transition probabilities were the ones that I had described in the previous slide. So with this, we are now in business because we can look at the n outcomes on these n participants. We know what test pattern was used on them. We also know what the outcomes are. And we write down the likelihood for the nth individual. We assume that these individuals are sampled from the population independently. So this is the likelihood that the nth individual's outcome is y of n, given that his test suite that he went through is t of n. And then we take the product across this. That's the likelihood when the unknowns are p. And what we try to do is find the p which best explains the test outcomes, and that's maximum likelihood estimation. So that's it. This is the strategy that we use to do the estimates. And this is actually a fairly straightforward problem because if you take the logarithm of this, then you have a sum of log of these likelihoods. And because this p was linear in the p, the log likelihood is concave in the p. So it has a unique maximum, which is easy to identify via a numerical procedure. So that's exactly what we did in the September serosurvey for Karnataka. We ran the antigen tests, the RT-PCR tests, and the IgG tests on some populations in the 30 districts of Karnataka. We had a more complicated design, but the design was known upfront. And so we used the design, wrote down the likelihood, and identified the maximum likelihood estimates. And so these were kind of the estimates that we see. This is the total COVID-19 prevalence as of September 16 from our estimates with confidence intervals. I'll now speak about the confidence intervals. But maybe before I do, the advantage of using classical statistical methodology is we can invoke some classical results and get some assurance that what we are doing is something that is reasonable. For example, under regularity conditions on the score function, which is the gradient of the log likelihood, gradient with respect to the unknown parameters p. These regularity conditions are actually fairly straightforward to verify in our model. The maximum likelihood estimate is consistent as the number of samples becomes large. So that means that your estimates are going to go to the true values in probability as far as our model is concerned. Under additional conditions, which are also rather straightforward to verify in our specific setting, these are all regularity conditions on the derivative of the score function, on the second derivative of the score function, and they are fairly simple to verify. We can say some things about the errors also. The errors, if you look at p hat of n minus p, that goes to 0. That's what this one says in probability. But if you lift up the errors, that is rescale the errors, then we have a central limit theorem. So that this converges to the Gaussian distribution with mean 0 and a certain covariance matrix. And this covariance matrix, it's a covariance matrix because we are doing a vector parameter estimation. Here the p hat refers to the vector of 3 parameters. So the covariance matrix is the per sample Fisher information matrix evaluated at the parameter p. So what this suggests is that if you look at the estimate p hat of n, the estimate p hat of n is normal if n is reasonably large or approximately normal with mean p, which is the true parameter, and then covariance, which is given by, we have a root n here, that's the scaling. So we bring it back there and write this as n times the per sample Fisher information matrix inverse. If you look at the estimates, they are random quantities, but their mean is likely to be p, It's a good approximation to assume that it's P when n is large. And the errors are essentially such that the covariance is given by n times the per sample Fisher information matrix. So this n times IPW is the overall n system Fisher information matrix, and it's just the inverse of the n system Fisher information matrix, which is a measure of our confidence intervals. Here is how we get the confidence intervals for the total disease burden. So that the Fisher information matrix gives us the entire matrix, but we are only interested in this estimate, which is the sum of the three. Now, its variance can be obtained because it's a linear combination. You can get the Fisher information matrix and then take this value associated with the linear combination, and that gives us the variance of the total burden estimate. And if you want a 95% confidence interval, you take your estimate and then look at this quantity, but evaluate it at p hat here. And this would be the standard error, and one plus minus 1.96 times the standard error gives us the 95% confidence interval. And that's what you saw in this picture. A little bit more about this Fisher information matrix. So I mentioned that the variance of our estimate is approximately, and it's approximate because that result of the central limit theorem is an asymptotic result. The variance is approximately U transpose this n sample Fisher information matrix inverse multiplied by U. So it's this value associated with this n sample Fisher information matrix is inverse. This n sample Fisher information matrix itself depends on what is the design as well as what is the current state of nature. So that's the IT of P, that's the Fisher information matrix per sample when the test suite T is used. There's a simple expression for this in terms of the expected value of the second derivative or a covariance associated with the score function, which is the gradient. That's the ITP. And then you weight it according to the number of people that have been administered this particular test suite. So that's the overall n sample Fisher information matrix. The WT itself comes from the design. So the variance is essentially given by, it depends on the design in this particular way. So there is a linear dependence on the WT, and of course, a dependence on P as well, and that comes through the per sample Fisher information matrix for when the test suite T is used. So why MLE? Before I expand on this Fisher information matrix a little bit more, why MLE? It has these advantages. For example, I told you about the variation in the test suites for a particular design. It naturally handles this variation. It also naturally handles or uses all the data that's available for a participant. I told you about enhanced evidence for antibody positive when the RT-PCR is negative and vice versa. So that's this remark here. Also, it handles noisy observations quite well because we are always working with likelihoods. Likelihoods naturally take into account noisy observations. And in the Karnataka Serosurvey, we actually had several transcription errors because of the way in which the samples were being handled. There was a lot of manual handling of the samples in terms of writing down the numbers that refer to the samples and linking it up with the samples which were sent to the lab. So there were some transcription errors there. And so we couldn't match up some of the samples. And when you have partial data, that is, we had the RT-PCR result, but we did not have the IgG results for some individuals. That means we have partial data. So the MLE naturally handles the partial data as well. When we don't have the IgG, we say that this sample did not have we couldn't get the IgG for the sample. And then when we run the estimation, we change the test suite on this individual and then run the MLE, and we get the best possible estimate that we can with the available data. Why MLE? There's another, the MLE reduces when we have only one test, and that's only the antibody test, and we are, let's say, looking at past infection. This is the usual one that's done for seroprevalence. Then there's, in that particular case, there is a closed form expression for the MLE, and that's the Rogan-Gladden formula. So that's given here. You take the crude estimate, what fraction turned out to be positive, and then you adjust that with the specificity and the sensitivity in this way. Sometimes it might be above 1 or below 0. You project it onto this interval, and that's the Rogan-Gladden formula. But it's exactly the MLE when there's only one test, and in that simple situation, we have a closed form expression. Otherwise, we have to essentially resort to a numerical procedure. So I'll now come to a performance given the design. So let's say that we have a design WT. The MLE procedure gives us an estimate and a confidence interval. The size of the confidence interval is a measure, could be a measure of performance, or equivalently, the variance of the estimate could be a measure of the performance. And smaller this variance, the better. And so the goal of the surveyor or the goal of the design problem, survey design problem, is essentially to minimize this. That's exactly what we have here. So here's the design problem. Given a budget cost C, so we have an overall budget within which we need to ensure that our test suites, etc., are picked. Given a cost CT for the test suite T, and we have this cost for all the tests, how many participants should be administered test pattern T in order to minimize the variance of the total disease burden? So this is exactly the design that we are looking for. And the optimality criterion is to minimize the variance of the total disease burden. Mathematically, this is called C-optimal design. Here is the disease burden estimates variance. So the disease burden estimate involves a linear combination of the underlying parameters. So that's the U. And it also involves the N sample Fisher information matrix and its inverse. And the N sample Fisher information matrix depends on the WT, that is the survey design, as well as what the current state is. And what we would like to do is we would like to minimize this particular variance across all possible designs, subject to constraints. So what are the constraints? So here is the cost of the design. We would like it to be within the budget, and the WTs are all positive. So I've tacitly moved from an integral WT here to real valued WTs, but that's because the usual budgets are such that these are reasonably large numbers. You can approximate the real, you can just truncate or round the real value outcomes to integral values and use them. Okay, so here is a concrete example that kind of highlights why we should solve this problem. So in this concrete example, I'm looking at a test suite 101. So what does this mean? We administer the antigen test, but we do not administer the RT-PCR test. We administer the antibody test. So the antigen test and the antibody test together cost about 450 rupees plus 300 rupees. That's about 750 rupees. On the other hand, here is an alternative test suite which administers only the RT-PCR test and the antibody test. But the RT-PCR test was more expensive, about 1,200 rupees in December. And this is about 300 rupees. So together, that's about 1,500 rupees. So what this suggests is when you compare these two prices, for each participant that we recruit here, we can actually recruit 2 participants and administer this test. Which is better? Would we rather have just 1 participant with this test and 2 parts for every participant here, 2 participants? So would you rather have 1 here or 2 of these? So that's the question that the survey design is essentially trying to solve. So I look at an instructive case, the instructive case of a single test. Let's just focus on the IgG. Again, let's say that we have a budget C and we allow only 1 test. That's the IgG test. And let's call its cost as C of IgG. So there's only 1 test and it's this one is 300 rupees. So if we administer N tests, then there is a natural estimate. So some of them will be positive, some of them will be negative. You look at the positive fraction. That's the standard estimator. And the positive fraction has a variance. That's P times 1 minus P divided by N, when P is the fraction of people that had suffered infection in the past in the population. If we have this particular parameter P, the analyst will have this information. So it is P times 1 minus P divided by N. Now, if you look at the cost of these N tests, well, each one is 300 rupees. I'm conducting N of them. It must be within this budget. So what's the maximum N that I can have? It's the total cost divided by 300 rupees. That's the maximum number of tests that I can do. And since the variance has N in the denominator, I must have as many samples as possible. So I must pick my N to be the total budget divided by 300 rupees. So that's this. When you plug that in, the minimum variance is P times 1 minus P into 300 rupees divided by C. So what this says is that the answer, which is the minimum variance, the margin of error is going to be proportional to the square root of this. The minimum variance is P times 1 minus P times 300 rupees divided by the budget. Now that is a picture like this, which kind of says what's the accuracy you can buy with the budget that you have. So if you have a budget C, the accuracy is this constant, which depends on the current state of the infection and the cost, divided by the budget. As P varies, of course, this particular quantity varies, but the true state of nature is the fixed quantity P, and you're trying to figure that out. And that would be a single curve here. So this is the behavior. And in this particular case, there is no question of what the optimal, the question of optimal design is very easily answered. You have to use all the budget, and there's only one test. You run your test on that many participants. But in the general case that I have highlighted, this is a general case, a similar behavior comes in. So the variance of our estimator is inversely proportional to the budget. So it's like this, it goes this way. But in addition, there is a design related control that we have, which can shift this up and down. And ideally, we'll choose a design related parameter, that's our survey design W, to keep this as suppressed as possible, so that for a given budget, the variance is the lowest. So that's exactly what we do. So here is a theorem that we can prove. Let V star be something which solves this abstract optimization problem. And you will see that this is actually similar to the variance minimization subject to the budget constraint, except that the budget has been normalized and we have it as 1. And I'll come back to interpret this. And the variance has had WT, IT, whereas now there is a normalization by a cost CT associated with the test suite as well. So let's look at this abstract optimization problem, and let's try to solve this abstract optimization problem. This A of VP is this picture. For a particular survey design, you will get a certain V, and that will give you this particular picture. And what we are trying to do is we are trying to keep this as small as possible. That's what this minimization of A of VP is. Then the optimal allocation is something that is to some extent independent of the survey. What is independent? The fraction of participants that use test suite T is sort of fixed. And as the budget increases, you just increase this in proportion to the budget. So it's given by WT star, the fraction that will undergo test suite T is given by VT star times C divided by CT. I'll come back to interpret this very soon. And the minimum variance is A of V star. We have suppressed this as much as possible divided by C. Okay, so the proof is actually fairly simple. So let's look at the objective function. So this is the overall variance that we wanted to minimize. And this was the budget. And all we do is substitute VT equal to WT CT by C. So I just pull the C over here and call the resulting variable as VT. And that VT can be interpreted as what fraction of my budget is actually spent on test suite T. That's exactly what VT is. And so if I know the fraction of the budget that's spent on test suite T, then this becomes clear, because if VT fraction of the budget is spent on test suite T, then the amount of money spent on test suite T is VT star times C. And if this test suite costs CT, the number of participants is just VT star times C divided by the cost of an individual's suite of tests. So that's the way to interpret this VT. Then once you do this substitution, you can go back and manufacture the VT here. So that means that we need WTCT by capital C. So you just multiply and divide by suitable quantities, and you will actually get VT ITP divided by CT. Okay. And once you pull the C out, you will essentially get the previous optimization problem, this optimization problem. So let's go back and examine this a little bit more. So you see that here is my Fisher information matrix associated with the test suite T. So this Fisher information matrix may be something that's very sharp in the sense that the curvature is quite large. And so the variance of our estimator can be made small. So that is the situation when we use, for example, the RT-PCR test and the antibody test. So when we run these two tests, you essentially have sharper estimates than when you use the antigen test. However, that sharpness of this particular test, that is the accuracy, should be discounted to some extent if the cost of this particular test is high. And that's exactly what happens here. If the CT is high, even though this test might be an excellent test, as far as our survey design is concerned, the cost is a little too high. And so you normalize it by this cost and then operate with that modified Fisher information matrix and the associated effective accuracy for that particular test, where the effective one is normalized by the cost. So that's the interpretation here. You might have an excellent test, but if it is too expensive, then you would rather not use it. You would probably use a poorer test just because it's cheaper. You will compensate for your poor accuracy by recruiting more participants. So that sort of highlights the proof. And that concludes the discussion about this C optimal design. I now want to maybe give one or two numerical examples and then speak about some extensions. So I'll just do one numerical example. So for this, we have built a tool, and I'm going to take you to that tool and demonstrate a design on that tool. So this is a tool that you can go to by getting to this website. It's called optimaldesign.readiness.in. So if you get to this website, you will see this particular tool, where you can enter what is the costs for each of those tests. And here I have entered 450 rupees for the antigen test. I have entered 100 for the RT-PCR test. The nominal cost is about 1,200 rupees. Maybe now it is a little cheaper. It's even cheaper if you do a pool test now. But let's say that in the survey that we were working towards, this cost was actually absorbed in a larger framework. So the surveyors did not see this cost other than the actual consumables cost. So let's put it at about 100 rupees, and the antibody test is 300 rupees. I will come to this notion called locally optimal design when I speak about the extension. So what we are actually doing is what is called locally optimal design. Then you enter the parameters, your best estimates for your P at this moment. So 10% of the individuals have active infection, 32.3%, let us say, have antibodies, they had past infection, and the fraction that have both, let's say, is about 1%. And then there is a design effect that one needs to take into account when your sampling is not perfect, when you're doing only systematic sampling and things like that. I've put it at 2.1 here. And then you can ask, what's the budget for a given margin of error? That's 0.05. Or alternatively, you could ask the question that we just solved. What's the margin of error or the variance for a given budget? So I'll solve the dual problem here. So let me click go. And when you do this, this thing runs and you will get an outcome here. So the outcome will be, one is test suite is 011. That suggests that you shouldn't do any antigen tests because the RT-PCR test is competitive. It's only 100 rupees, whereas the antigen test is 450 rupees and its sensitivity is poor. But you should run RT-PCR tests and antibody tests, and all of your tests must be of this variety. If I increase this cost to 1,000 rupees, the RT-PCR test to 1,000 rupees, and then I run this once again, you will see a new design now. Here is the new design. So it suggests that about 2/3, maybe 3/4, closer to 3/4 perhaps, should be RT-PCR tests and antigen tests. 907 antibody tests alone, and 642 RT-PCR and antibody tests. So that's the survey design. So we built this tool so that epidemiologists can use this. I'll now come to some other designs. So that's the numerical example. We have a couple of extensions. I'll just briefly highlight them. So what we solved here is something called locally optimal design. It's locally optimal because somehow the optimal design, the W star and the V star, will depend on the P, which is the true state of nature. But that's exactly what we are trying to estimate. If you don't know that, how can you assume a certain P? So typically what we do is we guess some P, and then we make a design for that particular P. But you could also do a more formal one where you say that I have only ranges for my P. So maybe my P falls in some convex and compact set. And now try to come up with a design that's a worst case optimal. So that is, you try to minimize the max variance where the maximum is taken across the uncertain P. So for this, we need to view the variance as a function of the design as well as the unknown parameter P. And it has the right properties. For example, for a fixed P, it's a convex function of the W, and we are minimizing cost. Yeah, so that's we are minimizing this variance. So yes, that's correct. And for a fixed V, it's a concave function of P. So we are taking the worst case, so we want to maximize with respect to P variable. And so it has the right properties. And so if the uncertainty set is compact and convex, if you close it, it's basically a compact set, but it could be an open set. For our designs, you can just close it and you can work with that compact and convex set. Then you can think of a zero-sum game and you can try to find the value of that game. This theorem says that the game has a value, and the equilibrium strategy for the player that is designing or choosing the design, that's the best worst case strategy. It minimizes the maximum variance. That's the 1022 is actually, so we have modified that to 1050 for our Karnataka Sero survey. That's the maximum across the unknown ranges for all the 30 districts. And so all the 30 districts have been conducting a test that's based on the outcome of this design. Okay, and there's another interesting problem. In the first Sero survey, what we identified was that the antigen test was more sensitive on those with symptoms and a little less sensitive than what we had assumed on those without symptoms. So it was 68% sensitive on those with symptoms and 47% sensitive on those without symptoms. Now, if upfront you know the fraction that are asymptomatic, let's call that R0, and the fraction that are symptomatic, let's call that R1, they might show symptoms not just due to COVID, but they might show symptoms due to other diseases as well. What's the optimal allocation policy when you know that the R1 fraction have symptoms and R0 fraction do not have symptoms? Now, this is an interesting question because when a participant presents himself, or when you recruit a participant and you find that this participant has symptoms, then you can choose a different set of suite of tests on this individual with symptoms compared to another individual without symptoms. And so what one could do is come up with an estimate based on the fractions that are symptomatic and asymptomatic. You make an estimate in each of these. So now the number of parameters doubles. So there are 3 parameters for the symptomatic fraction and 3 parameters P1, P2, P3 for the asymptomatic population. We call that as P of X. So X is 0 or 1. And then we make an estimate in each of that and come up with an overall estimate. And we then try to find its variance. So that expression is fairly straightforward. This is a linear function. So the variance comes out as R of X square times the variance of the individual estimate in each of these subpopulations. And then you try to minimize that. This can also be easily solved. The solution is to look at a C0 and a C1, budget on the asymptomatics and budget on the symptomatics, such that C0 plus C1 is 1. And then for this, you will solve the problem independently in each of these subpopulations. When you do this, you will get an overall performance, but that's a function of the split that you had, C0 and C1. And then you optimize that. That's also fairly straightforward. So the solution looks like this. The budget for the, let's say, the asymptomatic fraction is proportional to the fraction that are asymptomatic and also to the standard deviation of the estimate in that population. So if the population of the asymptomatics is higher, your budget for that is also higher. But if the standard deviation is higher, then too you will invest more money in that particular population to try to get a better estimate there. So fairly straightforward and fairly intuitive when you look at this. But if you look at the outcomes itself, it can be somewhat counterintuitive because it suggests that you should actually increase the usage of RAT on the asymptomatics. And that's somewhat surprising, but one can look at this. I'll not go into the detail here because I'm running out of time, but the optimal design gives interesting insights like this. So to summarize, what we did is we proposed a parametric model to enable disease burden estimation. We proposed an optimal design criterion for this total burden estimation. It was just minimization of the variance of the estimate. And we chose the classical C optimal design as our criterion, and then we solved this problem. Our solution told us what kind of accuracy that your budget could buy. You could also look at the dual of this problem, where you look at what's the budget that you need for a given accuracy. So that can also be straightforwardly solved. That one insight is that the test proportions don't change with the budget. but the numbers will be proportional when the budget increases. There are other criteria also. For example, if you want each of the 3 parameters to be estimated with some accuracy, you're not just interested in the sum, then there are some methodologies or objective criteria that were proposed by Chernoff as early as 1953. So he took the trace of the inverse Fisher matrix. There are other criteria as well, some weighted optimal design and things like that. These could be used to come up with optimal survey designs, and that's what we have actually used to design the Karnataka second round Karnataka Sero survey, which is actually happening right now. So thank you. I think that's where I would like to stop and open up for questions.
Thanks for that really interesting talk. I really like the straightforward and insightful application of the maximum likelihood approach that you used there. And so let me just skip to my question so I don't take up too much of this little bit of time. But my question is basically, could you strengthen the method that you developed by further partitioning the disease states? You have the 4 disease states you look at, but in particular, I'm thinking of one disease state that might explain some data that doesn't seem to be captured by your Ps, which is that early in disease, like the right before symptom appearance, it's pretty clear that the RT-PCR test will often come out positive, but the RAT will often not come out positive. And so there's sort of this discrepancy that isn't going to be captured by the maximum likelihood model that might be taken advantage of to gain just a little bit more precision in the inference. So that's just my question.
Yeah, so I think that's definitely a possibility, and we could possibly try that as well. We would have one more parameter to estimate. So the uncertainty, the confidence intervals may be a little poorer, but we might gain in terms of better, more accuracy. So this is a simple model. There is all. So yes, to answer your question, yes, we could do that. I'll also suggest one more that we'll probably take up, one more modification that we will take up. So for example, in our model, we had simultaneous antigen and IgG positivity possible. So a better model could be that this simultaneous positivity is not possible, but simultaneous RT-PCR and IgG positivity is possible, but antigen and this is not possible. So that could improve the estimate. This is closer to reality, just like the model that you have suggested as well. So these improvements could be tried. We are actually working hard with our state to get this data opened up. And also our code is, we are ready to put it up, but we are also trying to get the line list anonymized and put out for others to use. And I think we could try, I myself will try your idea, but there could be other such models that other individuals could try as well. Thank you for the
very, very interesting. I just add one more comment, which is just, I think there are a lot of data sets like the line list that you have in various contexts everywhere. So I just applaud you for making that available as soon as you can, because I'm sure people will make use of it.
So really wonderful talk. I really enjoyed it, and I'll get back with questions after reading. So one question I had, this is not immediately related, but so there is a different delay for each of these tests, right? So if you think of this in a more restricted context, like maybe a hospital and where you want to do like surveillance with minimum delay. So have you thought about that kind of question? And
that's a very important point. In fact, the antigen test, for example, is something which can be done at the point of care. And immediately, if the person turns out to be positive, you can immediately provide the care that that person might need, quickly isolate the person. So there are many advantages to this quick outcome. Whereas the RT-PCR test takes about 24 hours. It's probably shorter now, but in the survey that we conducted, we noticed that there were actually quite a few delays, particularly in the distant districts away from Bangalore. So the median time was 3 days for the results to come. So it's very important to take this into consideration, but how to do that requires a little bit of thought. I haven't given much thought to it. It's an important question. I just kept it for a little later. So I'll be happy to give it a little more thought when I have time and then get back to you on that.
But I just want to thank Rajesh again for talking today. And thanks everyone for attending. Hope to see you in 2 weeks on March 11th for our next seminar.
Yeah.
Thank you.
Thank you very much.